proceeding to our next speaker, Professor Sasaki is the project scientist of the Kaguya mission. That means he is responsible for the scientific instruments on board, which means he knows really what's going on. You've all watched the beautiful TV pictures that came down from this mission. He will tell you the science that's behind it. Professor Sasaki works for the Institute of Space and Astronomical Science, ISAS, which is now part of the Japanese Space Agency, JAXA. He was one of the pioneers in designing this mission, which at the early times was called Selene, and he was involved in the very first studies in 1996. He followed it up since, and he is the most suitable person to give you the accounts of what has happened. Please, the floor is yours.
Thank you very much for introduction. I'm very proud and I'm very happy to introduce our Kaguya this special event. This evening I'll show you the first the mission outline of Selene, and then after that I'll show you some recent results from the our mission Kaguya. So first I'll show you the Kaguya mission objectives. The primary objective of the Kaguya is the lunar science. So that is a global survey of the moon to study the origin and evolution of the moon by observing the elements and also minerals on the surface, and also the surface structure and subsurface structure and the gravity field, magnetic field, everything. So that is the primary objective, and also these data are used for the future moon utilization activities. That is the second objective. And third one is the technology development for the next step lunar exploration. And also the public outreach is very important for us. And for Kaguya, we'll take the movies of the beautiful Earth and also the beautiful lunar surface. I'll show you the movies later. Okay, here is the Kaguya configuration. So the Kaguya consists of the three spacecrafts. Main satellite in the center of the picture, there's a main satellite, and also we have the daughter satellites, 2 satellites over there. So we have 3 satellites. And the external view of the main satellite, you can see the solar panel that generates 3.5 kilowatts power. And also you can see the dish over there, that is a high gain antenna. So the data is transmitted to the ground very high speed, 10 megabps. And also the mission instrument, there is a mast, 12-meter mast. That one, that is used for the magnetometer. And also we have the antenna, 50 meters antenna extended from the main body. That is used for the radar sounder experiment. I'll show you the data later. And the right-hand side, the Kaguya, the size, the weight is almost 3 tons. That is very heavy for us. And the size dimension about 2 meter, 5 meters. So that is a large satellite. And the orbit is the 100-kilometer altitude, and the inclination 90 degrees. That is the polar orbit to observe the global map, to make a global mapping of the moon. And we have daughter satellites. That is named. They are named Okina and Ona. That is all the traditional Japanese name. And that they are very small satellites. That they are 50 kilograms. And the size is just 1 meter scale. So they are very small. And the orbit is 100 kilometers by 2,400 kilometers. That is the elliptical orbit. That is one Okina satellite. And for the owner, we start, that is the 100 by 800 kilometer elliptical. Anyway, these two sub-satellites are used to study the gravity field of the moon. Okay, here shows the mission instruments, scientific instruments. So there are plenty of scientific instruments. I don't go to in detail here, but for the science of the moon, we observe the element abundance and mineral composition and topography of geological structure, gravity field, and magnetic field using the 11 instruments. And for the science on the moon, to study the radiation environment, plasma environment, and also the ionosphere of the moon, we have 3 instruments. And for the science from the moon, to observe the solar terrestrial plasma environment, we have 2 instruments. And also for the publicity and educational purposes, we have the high definition TV cameras. So we have many instruments. And this slide shows the configuration of the onboard instruments. The blue ones are the mission instruments or scientific instruments, and others are the bus subsystems. So the you can see the right-hand side picture. The orbiter moves in this direction or in this direction, and keeping this left side face the lunar surface all the time, using the 3-axis attitude control. So almost all instruments to observe the lunar surface are attached to that plane. That is the configuration. And we carry not only the instruments to the moon, but also we carry the people's wishes to the moon. That is the Wish Upon the Moon campaign, in which we collected 400,000 persons' names and message from Japan, from the whole world. They are also delivered to the moon. Okay, road to the moon. That is actually it's a very long way for us. Oh, okay, please. Anybody have a pointer? Then it's easy for me to explain. Thank you very much. How to use this? This one?
No, that's the...
That.
So it's the first one. This one.
Okay, this one. Okay, thank you very much. Okay, so the road to the moon again. So the after the launch, that was the September the 14th. We had phasing orbit like this twice around the Earth. And then we reached the lunar orbit. It took 14 days to get there. And here is the lunar orbit insertion, the LOI. That is the most critical operation in our operation. And first we had the elliptical orbit. So the apogee was lowered by the orbit maneuvering operation several times. And finally we got the circular orbit, mission orbit, and the inclination 90 degrees. And during the orbit transition, we separated the 2 sub-satellites. And immediately after reaching the mission orbit, we extended the mast for the magnetometer and also extended the 4 antennas. That is the initial operation. And I would say all operations are conducted very accurately and perfectly, I would say, and just on time. Okay, here shows the high definition TV system. Actually, we have 2 cameras. One is the wide angle camera, and another one is a telescope to observe the beautiful Earth and also to observe the lunar ground, the lunar surface. Now I'll show you the picture, motion picture. Just a minute. Okay, so in this case, we are flying over the South Pole. So the Earth is seemingly going down and falling below the horizon of the lunar surface. So in this case, the South Pole is here, and the North Pole is here. And if you have good eyes, you can see the Australia and also the Asia. And this motion picture was obtained, say, the November the 7th. It's a rather initial phase of the mission operation, and so we are very, very pleased to see this picture for the first time. So the Earth is going down. And next, I'll show you the Earth drive. Okay, in this case, we are flying over the North Pole of the Moon. So here the Earth, and in this case, the wide-angle camera is used. So the actually this Earth is smaller than the previous one. So in this case, the North is this side of the Earth, and you can see the typical crater here. This is a 100-kilometer size. Now, usually the 100-kilometer size crater has a central peak, or the exact name is I don't know, but there is a peak inside the crater that is generated by the impact. That is a very typical one. Anyway, we can see this kind of a very clear image using the high vision TV. I'll show you that one. That is a rather fast channel, so you can enjoy it. Okay, in this case, we are flying over the Sea of Serenity. That is located in the northeast portion of the Moon. So in this case, the playback speed is 8 times, so you can enjoy the flying over the Moon. Just a demonstration. Okay, now I'll explain the how much time I have? 10 minutes. Okay. So now I'll explain the scientific results. This evening I'll show you the data from the multi-band imager and terrain camera, lunar radar sounder, and relay satellite experiment. Of course, we have plenty of data, but this evening I'll show you. Okay, first is the multi-band imager. That is the UV visual IR imager with the spectral bandwidth from 0.4 to 1.6 micron using 9 filters. and spatial resolution 20 meters, and this is the instrument. And so this instrument is to characterize the lunar surface, or to characterize the mineral assemblage of the lunar surface. This shows the how to characterize the mineral assemblage. Here is the wavelength, and here is the this axis is the reflectance of the sun, right? So by measuring the reflectance of at 9 positions or at 9 wavelengths, we can characterize the reflectance characteristics or characteristic features. So that reflects the surface material. So we can know the chemical assemblage of the surface by this method. Okay, this is the typical data. This one is the 20 kilometer by 20 kilometer picture, and the resolution 20 meters, very high resolution. And the observation spot is here, about 1,000 kilometers from the famous Oriental Basin. And here shows the Clementine UV visual image. You can compare them. So the you can see the very clear image for the multiband image. The resolution 5 times, so you can identify. You can see the effect of the higher resolution. And this shows the color processing of the data. This one is the pseudo color image using 3 lines, 900 nanometer red and 750 green and 415 blue. So you can see the very clearly the existence of ejectors out of the crater here. And this case, this one is a color ratio image. That is the 750 nanometer intensity divided by 1000 nanometer intensity. Then we can get new information by that processing. That characterizes the this picture characterizes the distribution of the ejectors. You can see the yellow, red, and green, and so that is the new information using the this kind of processing. And next is the terrain camera. That is another imaging instrument for Kaguya. We have 2 cameras, forward and backward, and that is a stereo camera. So the spatial resolution 10 meters, and this is the camera. I'll show you the typical example here. This one is a 16 kilometers with a resolution 10 meters. So the observation spot is here, just close to the South Pole, and so you see the very clear image. And this yellow area is expanded. Next slide. This one is expanded, but still. This one is a 3 kilometers, and still you can see the craters very clearly, which can be compared with the Clementine high-resolution camera for the same spot. So you can identify the smaller craters and also the fine structure inside the crater. So there's a big difference. And as I mentioned, the terrain camera is the stereo camera. We, by data processing, we can get the 3-dimensional images like this. This is a famous Dyson crater here, and the 3-dimensional image. The Dyson crater is located here with respect to the North Pole. The location is here. So we can get this kind of 3-dimensional image over the sphere in the mission. Okay, let's move to the lunar radar sounder experiment, 3 minutes or so. Okay, 5 minutes. Okay, that is used for the mapping of subsurface structure. And this shows the principle of the observation or measurement. The orbiter transmits the high power electromagnetic pulse to the ground. and we try to observe the reflected electromagnetic waves, although they are very weak. And then we can get the information on the surface structure. We use 800 watt power and also the 5 megahertz frequency for this experiment. And this is an example of the result. So in this particular case, this red line is the ground track for the observation. That is located in the northern eastern part of the Mare Imbrium. And there is a small crater just close to the ground track. And here is the data of subsurface structure. And that is obtained by the synthetic aperture radar technique. And here is the depth. So 0 is the surface of the lunar. And here is the time corresponding to these numbers. So you can see there are some layer structures here, which are enhanced by the red lines in the lower panel. So this is very promising result for us, because we can get this kind of subsurface structure over the sphere for the 1-year mission. So this must be the new result in the lunar exploration. Okay, this is another experiment. That is a 4-way Doppler measurement experiment. That is also giving very exciting results. This shows how the mechanism, or how to observe, how to make the 4-way measurement, 4-way Doppler measurement. So when the main orbiter is behind the moon with respect to Earth, we cannot get contact directly. But if we use the relay satellite, then of course we can get the contact with the relay satellite, and the relay satellite also is, so as you can see, the relay satellite can get the contact with the main orbiter in the far side. So in this configuration, we can know the Doppler shift of the main orbiter. So the Doppler shift frequency includes the information of the gravity field in the far side. So this experiment is very unique, and that has not been conducted so far. So this just shows the coverage of the gravity of the observation in that configuration, and this black dot means the observation area. And the background is the map of the gravity anomaly, and the far side, near side, very clear image we have already obtained, but in the far side, very poor information now. But we have a lot of coverage these days, and already the more than quarter coverage we have already obtained, and suggesting new findings. Okay. I'm closing now. So this shows the operation schedule. We are here, and the nominal observation is continued up to the end of this October. And we hope some extended mission, half a year or so. That is now under discussion. And all data obtained here will be open to the scientists all over the world 1 year after the termination of the nominal operation. That means all data will be open by the end of 2009. So this is the actual last slide. So the concluding remark. The scientific observation is underway as planned, and the major scientific goals we have initially set are expected to be fully achieved by the end of this year. And the extended mission will be conducted for further routes. And we are now rather confident to contribute greatly to the lunar science together with other lunar missions, Chang'e, Chandrayaan, and LRO. And finally, international collaboration for new lunar exploration and utilization for human society is now on the horizon. Thank you very much.
Thank you very much for this really exciting talk. There is really much more than just TV pictures. There is very serious science coming out of this, and we would like to congratulate you for these fantastic results.